Let's now extend our knowledge of equivalent circuits from Cartesian coordinates to curved coordinates. Based on what we learned before, we would define the effective heat transfer coefficient as Q double prime equals H effective times a temperature difference. What is inconvenient about this in curved coordinates is that Q double prime is not constant as it was in the planar case. Q double prime depends on the radius due to the change in cross-sectional area as a function of radius. So what would work better for us here is to define this based on the heat current instead, which is constant as a function of the radius. So we have then Q sub r, and we can set this equal to an expression that is based on the radius at 1 or the radius at 2. Q sub r is a constant. T sub 1 minus T sub 2 is also a constant. And since the area at 1 or the area at 2 have different values, this means that the heat transfer coefficient defined at radius 1 or the heat transfer coefficient defined based on radius 2 must have different values. This is important because it means that in curved coordinates, we have to always define a reference surface. The effective heat transfer coefficient for that medium between radius 1 and radius 2 depends on whether we've defined a reference surface at radius 1 or at radius 2. And we can see that here very clearly, that this expression and this full expression have the same value overall, but because the cross-sectional area, A sub 1 and A sub 2 are different, it means that we have to be explicit about the reference surface for the heat transfer coefficient, whether it's at surface 1 or at surface 2. So let's look at this more explicitly. If we use reference surface 1 at radius 1, we can derive at that coordinate the heat current divided by the cross-sectional area. The heat current divided by the cross-sectional area, which is essentially a flux, is then given by this expression, which comes from Fourier's law, that we have minus k times dt dr evaluated at the radius r sub 1. Here we're going to now plug in based on the expression that we found a moment ago for pipe insulation. If we plug in with that, we then get this expression here. And by looking at this, if we separate out this contribution from the temperature difference, we then have a thermal conductivity and a few other quantities based on length scales in the denominator, which together contribute to the effective heat transfer coefficient defined at radius 1. So we have then that the effective heat transfer coefficient at radius 1 equals k divided by this quantity of r sub 1 times the natural log of r sub 2 divided by r sub 1. We know that the resistivity, which we have to define now at this reference surface 1, is R double prime effective at reference surface 1 equals 1 over the effective heat transfer coefficient at reference surface 1, and that then equals this expression shown here at the bottom. Here we have implemented reference surface 1 because this flux was evaluated at R equals R sub 1. But we could do this instead with reference surface 2 as well. So if we use reference surface 2, we would instead evaluate that flux at R sub 2. That means that here in the denominator, instead of R sub 1, we have R sub 2. We can define then the effective heat transfer coefficient based on reference surface 2, in which case the only difference is that instead of a value R1 here, we have a value R2. And then finally, we can define the resistivity based on reference surface 2. This is just the inverse of the effective heat transfer coefficient at reference surface 2, which gives us this quantity. Now, what's important to emphasize is that whether we use reference surface 1 or reference surface 2 is simply a choice. and it will give us the same answer in the end. So if you take these two effective heat transfer coefficients based on radius 2 and on radius 1, and you plug that back in over here, you will find that they both provide the same heat current. So we simply need to choose one reference surface, make sure that's explicit, and that we understand that that impacts the value of the effective heat transfer coefficient. But then in the end, irrespective of our choice, we'll get the same answer.